The static structure analysis and formal verification of SoC with software safety mechanisms for functional safety. Destruction. The fourth campaign in large SoC designs are complex and critical for ensuring the reliability of software safety mechanisms. This paper represents an integrated approach using static and structural analysis and formal verification techniques to detect the resolve faults early in the design process. By integrating this method, we aim to enhance the diagnostic coverage and ensure compliance with automotive safety integrator level ASIL requirement for our methodology involves a multi-step process that includes gap analysis and static structural analysis and formal verification to identify and mitigate the potential faults. A case study on Samsung's automotive project demonstrates the effectiveness of this methodology, showing the improvement in fault detection and resolution. The result highlights the importance of combining static and dynamic approaches to achieve the comprehensive diagnostic coverage and ensure the highest standard of the safety reliability in automotive systems. Introduction. Conducting fault campaigns in large system on chip SoC chip is a tedious and challenging process, as the early detection of faults in the semiconductor circuit is crucial for ensuring the reliability and effectiveness of the software safety mechanisms. This paper presented the benefits of the using software safety mechanisms and software task libraries in an IC design to improve the diagnostic coverage. We will talk about how software test libraries STLs are used in functional safety and ensure the correctness of software safety mechanisms, and how to apply an integrated approach to prove diagnostic coverage using both static and dynamic fault analysis through the innovative structural analysis and formal verification techniques. This paper aims to how this methodology improves the detection and resolution of faults and overall safety and reliability of the SoC designs. Our approach not only identified fault in early stage, but also provide a framework for a continuous improvement in fault detection and general resolution process. Chapter 2. Background, software safety mechanisms. Section 8, definition. Software safety mechanisms. Using software safety mechanisms attempt to protect a design targeted for automotive market has become a popular approach for ICs and SoCs because it facilitates a structural and effectiveness approach to achieving the coverage metrics, and software systems have benefits such as one, flexibility. They can add it to an existing safe related ICs after tape out the production to increase safety coverage gaps without really spinning the whole IC. Just 2 is consistency. This ensures the consistent code across different components in the design projects or systems. 3, efficiency. They save time in the tests developed, allowing teams to focus more on safety and analysis and writing new code. 4, real-time monitoring. As many include monitoring tools that check the system performance, allowing for immediate detection of the anomalies. 5 is improved documentation. They help ensure thorough documentation of safety requirements which aid in traceability in audit. And 6 is contribution to ASIL metrics. They contribute to the ASIL metrics for ASIL level A through D. 7, a saving on the hardware footprint. They save chip real estate and cost. And typically, components of the software safety mechanism include software test libraries and self-test libraries. Software test libraries ensure the safe access to memory region and facilitate reliable data exchange between the different parts of the system and monitor system health. B. Definition. Software test libraries. Software test libraries STLs are used to test, validate, and ensure the software safety mechanism correctness during the systematic testing. STLs are beneficial for testing software safety mechanisms because they are 1. Reusable. STLs provide a collection of reusable test components, frameworks, and tools that can be reused across different designs and projects, which streamline the testing process. 2. Efficient. Using predefined software library saves engineering time and helps meet deadlines while ensuring ISO 26262 compliance. 3. Traceable. They help in the tracking, test, and coverage used throughout the development used as a work product for audit and certification. 4. Consistent. They provide a set of standardized tests for a consistent and expected result. Standardized test for consistent expected result. 5. Standardized. Okay, they deliver standardized testing method that align with the safety process defined in the ISO 26262 standard. For this paper, we will refer to all of these as STLs, which are used as the software safety mechanism of functional safety. C. Execution of the software safety mechanisms. Software SMs can be executed in several ways. Some popular methods are build some software SM code as a binary and load it in a terminal, internal RAM or ROM. It is preferable when the STL function size is small. Build software SM code as binary and load it to the external DDR. This approach is best when the RTL function size is big. In Figure 1, the software SM can be loaded into both internal RAM and DDR memory. This mechanism will protect 4 different modules. The DDR controller prefers video system and audio system. This is Figure 1 is a simplified structure of the complex SoC system. Chapter 3 is structure analysis and formal verification to provide a diagnosis coverage. As mentioned above, implementing effective software SMs safety mechanisms can significantly contribute to meeting the target requirement of Acer metrics. If the diagnostic coverage provided by these software SMs can be evaluated in the early stage of the implementation, the effectiveness of the mechanisms can be pre-validated. Structural analysis and formal verification techniques can be employed to achieve this. Structural analysis focuses on identifying design patterns and protocols that reduce the scope of proof. By leveraging formal verification, we can evaluate the failure state without requiring simulation execution or dependency on software stack readiness. This technique allowed for an early proof of concept for software safety mechanisms even before the complete software stack is developed. The process involved the 3 key steps. A. Gap analysis to identify the area for coverage improvement. By reviewing the target fault space and design, we can identify areas where coverage improvement is possible through software SMs, rather than relying solely on pre-existing hardware SMs. Figure 2 shows the full matrix through a software SM, rather than relying solely on a pre-existing hardware SMs. Figure 2 shows the full matrix interconnection when each slave port can access all the master ports depending on the address range. Pre-existing hardware SMs implemented in master IP, slave IP, do cover the entire bus matrix. The uncovered areas are where software safety mechanisms need to be implemented to achieve coverage improvement. The Figure 2, AXI interconnect bus matrix and the IP connection. B. Static structural analysis to prove protocol connectivity. Once the target area for coverage improvement is defined through gap analysis, The connectivity of this target area can be verified using static structure analysis. GMC EDA Safety Scope TM can be used for the static structure analysis. Safety Scope supports multi-pool analysis, structure analysis modes, including connectivity analysis and data path analysis. We refer to this as a river flow mode RFM analysis of a safety scope. B1 RFM analysis basics. The RFM analysis is a data path coverage and RFM analysis is a data path coverage analysis that assigns safety mechanisms coverage to the entire data path from the generation GEM point, where the data is generated, to the check CHK point, where the data is consumed. GEM point and checkpoint. Figure 3. RFM analysis of the safety scope. GEM point and checkpoint. B2. Data path analysis. In data path analysis, we do traversal backward from the checkpoint and mark all visited logic. 2. Traverse forward from the GEM point and mark all visited logic. And 3. Identify the logic that appears in both forward and backward traverses at the intersection. 4. To isolate the logic that is part of the data path only, remove all covered registers, latch banks with less than the RFM underscore filter underscore width. 5. Repeat step 1 and 2, but only traverse through the preserved registers and latches identified in step 4 for multi-level paths. The logic-on that remains after this analysis will be considered part of the data path. B3. Structural analysis for a target data area. The target area shown in figure 2 is part of data path. If we zoom into the internals of the crossbar, we see the following data packet flow as in figure 4, figure 3, and figure 4. Figure 4 is data packet flow and the bus matrix. So in data 1, data starts as a user packet, for example, AXI transaction at slave 0, which is connected to the crossbar. 2. In the crossbar, the user packet is converted to an NOC packet by the protocol converter engine, user to NOC. 3. The crossbar then routes the NOC packet, routes the NOC packet to the appropriate master 0 NOC interface, NOC to user. 4. The packet is converted back to the user packet and sent to master 0. 4. The main remains intact throughout this path, which is essential for the safety scope data path algorithms. Using safety scope RFM, we extract all the data path nodes that can be covered with data path protection and software safety mechanisms. This list is then provided to the formal verification engine to prove the coverage. C. Formal verification of the reduced space to prove full coverage. GMS EDA CASTA equivalent RTL is used as a formal verification solution to prove whether the stop at 0 or the stop at 1 permanent faults are detectable or not. This basic idea involves comparing the number RTL and faulty RTL through a formal equivalence check. This process closely resembles the faulty injection at a specific point within a conventional faulty simulation procedure. As shown in figure 5, the normal RTL is compiled as the design unit named spec, while the faulty RTL is compiled as a design unit named IMPR. To proceed, the prerequisite materials include the RTLs of the model, of the module, the address map of the bus interconnect, design architecture, the target fault list, and the formal verification tool has the equivalent RTL. While various other static and formal verification solutions available in the market could potentially be applied to this methodology, we chose Siemens EDA safety scope and case the equivalent RTL for this exercise enables seamless integration with the safety analysis, static analysis, and formal verification. The main procedure is as follows. 1. Configure spec as a top module. 2. Configure input as another top module. 3. Select a fault injection point from the fault list. 4. The implement design set the selected faulty point as a cut point and drive to 0 or 1. So it mimics a stuck at 0, 1 permanent fault. 5. Map the detection points and the long-form verification engine to compare and find the result. 6. Repeat this process until all ports in the list have been evaluated. So the formal verification result shows in 3 ways. Fired. In the original use case of the CASTA equivalent RTL, this means that two designs have differences in this exercise and indicate the faulty point causes the deviation at the detection point, making fault detectable. The counterexample waveform shows evident that the fault injection point is causing the deviation. Proven. The fault point does not cause any deviation at the detection point. This result indicates that the fault point is not detectable. Inconclusive, formal verification tools cannot resolve to proof or firing within the specified time. Figure 5 configuration and operation flow of formal verification with the CASTA equivalent RTL. This approach is applied to the AXI interconnect bus matrix in Figure 2, which is reduced design scope for the structural analysis. If the location of the multiple faulty points differ, the detection points, mapping points of CASTA equivalent RTL also vary accordingly. In this experiment, faults are propagated to the endpoint through the AXI channel, causing difference at outputs of the AXI port, which are considered detection points. After CASTA equivalent RTL catches the deviation, the result is reported as fired. Table 1. Target area and corresponding detection points. As shown in Table 1, if fault point is W data in the slave 0 interface area, the detection point should be set to the master 0, as specified by the address map. The AXI bus communicates using valid and ready signals in a handshake method, so the valid ready signal should be given as a detected condition at the detection point. Beside the data and address signals listed in the table, many types of AXI bus sideband signals can be analyzed in the same manner as the data signals. In practical applications, multiple bus interconnects are used. In typical SoC design, there are numerous bus interconnections, and the master side of an IP can access many slave IPs. It allows the CPU software safety mechanism to prove diagnostic coverage, and the formal verification tool can detect the faulty propagation path to the endpoint connected to some slave IPs. However, appropriate constraints need to be applied for the formal verification tool to report the accurate results and improve the runtime. Below are how we used constraints for this experiment. For my VIP for AXI, we attached request a formal library QFL to constrain control points to be AXI protocol compliant. The QFL includes formal assumptions. For example, it ensures that the data address does not change during the valid asserted time and the ready signals is the asserted black box. And most designs, a module has many sub modules not within the cone of influence (COI). We can remove these modules to reduce runtime. However, only validated modules can be block-boxed since some can cause false results. Apply constants for the unused slave master port. Unused ports should be tied to 0 or 1. Untied ports can cause the formal verification tool to generate unnecessary packets leading to incorrect results. Clock reset for clock domain crossing points in asynchronous bridge. Sometimes the clock domain crossing domain points makes the formal verification tool difficult to pass packets through them. The exact clock and reset settings are needed for this point. There are expected limitations to this formal verification methodology. First, considering a fault in an address path, the fault propagating through the address path cannot reach the appropriate port. Hence, the result for the address cannot be fired. It can be proven or inconclusive. Second, if a fault is injected into handshake signal like a valid and ready, the entire transaction delivery can differ from the original. Therefore, the fault path may be undetectable, even if the formal verification result is reported as fired. Despite this limitation, there is a potential to further extend the application of this method beyond the practical experiment being discussed. Although this experiment only addressed permanent faults, it can be easily extended to the analyzed transient fault injection. Transient fault can be mimicked by applying appropriate sequential assumptions as a constraint instead of driving the faulty point to 0 or 1. The chapter 4 is test data analysis. The above approaches were applied to improve coverage gaps in dynamic fault simulation in Samsung with the goal of achieving automotive safety integrity level as a requirement for an automotive project. A. Diagnostic coverage achieved using the traditional fault simulation techniques. At Samsung design, traditional fault simulation techniques were employed to address a total of 6,000 statistically random sampled faults. This paper are my fault campaigns provide accurate result for ISO 26262 certification. Presented at DVCON US 2024, describe how we planned and verified the fault campaign activity on the design. The results on this fault campaign, detailed in Table 2, are from the latest fault campaign with fully configured safety mechanisms, which is up to date from the result published in 4. Table 2. The practical experiment in this paper addresses the process of meeting the DC target for A through B through the analysis and additional experiment, not detected, residual, not deviation, not injected faults. Traditionally, faults in the no deviation and no not injected categories are considered safe. However, taking a conservative approach, we conducted engineering analysis and a judgment on 33.50% of the not detected categorized faults. Through the judgment work of the designers and verification engineers, we obtained a safe judgment for a 6.76% in the residual category and 15.95% in the no deviation category. Most cases were judged safe as a designer confirmation, and the faults propagated through unused paths due to a lack of verification scenarios or unintended scenarios, which do not occur in actual use cases. As shown in Figure 3, despite significant effort after judging 22.71% as safe, approximately 11% of the total ports remained conservatively unsafe to achieve the ACE-B target, considering a margin of error (MOE) of 1.06%. An additional effort of around 3% was required. Table 3. Result of engineering judgment. Section B. Final coverage goal achievement. Through a gap analysis of not safe faults, we identify a gray area that hardware SM could not cover, accounting for 4.88% of the total. To improve this 4.88% and achieve the remaining 3% coverage required for ACE-B, we collaborated with a software engineering team to apply the software SM. The software SM was developed and implemented by the software engineers following the guidance of the hardware designers. The read after write RAW safety mechanisms was specifically considered with the STL in this experiment. During discussions with the software team, we excluded some fault paths from the target application due to their location and the flash memory area, where the low RAW-SM could not apply. Consequently, we proposed coverage for 4.47% through the software SM from the total uncovered fault of 4.88%. To prove the coverage of these faults, we opted the static analysis and a formal verification instead of a traditional fault simulation, which has difficulties preparing the necessary input stimuli. First, we verified through the structural analysis that RAW-SM had no structural restriction covering specific target faults. Then we conducted a formal verification to confirm that the actual valid RAW operations could detect these faults. Following the previously described flow, we performed the structural analysis and formal verification using safety scope and Casta equivalent RTL and confirmed that 4.41% of the faults were covered by the software SM. As a result, as shown in Table 4, we could claim the 93.62% coverage for the NOC in safety island for Samsung design. Table 4. Result of static and formal analysis. Chapter 5. Limitation and future works for further extension. This methodology outlined in this paper facilitated the earlier analysis of the coverage for software safety mechanisms. It focuses explicitly on data path protection, although this approach can be extended to other use cases, such as controller path protection or software safety mechanisms within the appropriate observation points. We will restrict the formal verification to a specific sequential path rather than encompassing design hierarchies. Future works on this approach include 1. Creating design cones must be addressed using safety scope RFM method to limit the design size that needs formal attention. 2. Create a seamless communication between the design partitioner, safety scope, then a formal verification engine so that the setup needed for the formal verification is auto-generated. 3. Exploring the possibility of the dynamic formal analysis based on the input stimulus to reduce the target design space. The proposed methodology is suited for any SM that needs proper vectors to prove it. For ACE level D, if the application is used to achieve the ACE level, and the other approaches will enable faster proof. However, If the software SM is used to achieve some of the coverage goals, this approach will help in faster closure for software write-up with early metrics and identifying the area that are not covered using software SM models. For other Acer levels, this approach can be used to prove the effectiveness of both hardware and software safety mechanisms. Chapter 6 Conclusion. Structural analysis and formal verification allowed for enhancing the fault detection resolution without the need for a traditional fault simulation process. In this paper, we presented a methodology involving multi-step processes, including gap analysis and static structural analysis and a formal verification, to identify and prove the fault resolution early in the design process. A case study on a Samsung automotive design highlighted the effectiveness of this approach, demonstrating that we achieved the comprehensive diagnostic coverage for the target Acer goals by combining static and dynamic analysis methods. Through our partnership with the Genius EDA, we aim to automate and integrate this methodology into their functional safety solutions, thereby significantly enhancing the overall safety and reliability of the automotive system verification. All static of the dynamic and analysis, including the value engineering judgment, should be managed within a single database and fully automated to report the final metrics. By continuously improving our approach, we strive to stay ahead of emerging challenges and ensure the highest standards of the safety and reliability in SoC design. Reference is just 5. Okay, today I read this paper, the structural analysis, static structural analysis with formal verification of SoC software safety mechanisms for functional safety, from the DVCON2025. Today, thank you for your time and see you next time.